All right, thanks again, and thanks for the invitation to this little workshop that has proven wonderful so far. I will be talking about singularities within the framework of shape dynamics. And my talk will be about a bunch of work that I've been doing with different collaborators, mainly Tim Koslowski and David Sloan, and also my students, Martina Adamo and Rishabh Jha. And I will also mention work done, for example, by David alone and other collaborators. So gravitational singularities, this is the kind of picture that we have had for a while of singularities in classical general relativity, a region of space-time where more or less we don't know what happens. This is a cartoon picture, of course, but it's to illustrate a quite precise problem, which I want to focus on, because singularities might represent a problem for our description of physics from several points of view. The one that I'm more concerned with is determinism. This is a quote from a 1976 paper by Stephen Hawking. He wrote that a singularity can be regarded as a place where there is a breakdown of the classical concept of space-time as a manifold with a pseudo-Riemannian metric. Because all known laws of physics are formulated on a classical space-time background, they will all break down at a singularity. This is a great crisis for physics because it means that one cannot predict the future. One does not know what will come out of a singularity. So this is the problem that I'm interested in, whether determinism, the fact that one can predict the future from initial data, breaks down for real the singularity or not, and whether we need quantum gravity in order to solve this problem or not. The expectation among a lot of physicists has been that probably we need quantum gravity in order to smooth out the singularities that general relativity predicts. And the intuition they use comes from classical electrodynamics, in which one can calculate the self-energy, the electromagnetic energy of, for example, a spherical distribution of charge. And this is something that diverges if we shrink the charge distribution to a point. However, this very same singularity is resolved in quantum electrodynamics because essentially of the uncertainty principle that does not allow you to localize a charge beyond a certain level. Any calculation involving time and diagrams studied in basics quantum field theory courses shows that the total energy can be resolved to a finite value. So there is this expectation that something like that might be the solution to the singularities of general relativity. However, a point charge that is added by n to the electromagnetic field is a quite different concept from what we see from gravitational singularities. These are a phenomenon that happens even in absence of sources, and we don't have to put any idealization like a point particle by hand. It's something that just the equations of motion or even free gravitational fields without much sources evolve into. So let's look at the issue more closely. Why do we say there's something wrong at singularities? Well, for one, the volume of certain spatial hypersurfaces goes to zero. That's what you see in an FRW, for example, cosmology. That's the first sign that there might be something going on. More precisely, we see that some eigenvalues which are invariant objects of the energy momentum tensor, diverge. And probably the most popular and most precise detector of a singularity is when curvature invariance of space-time at a divergence. Now, the question I wanted to answer is, does shape dynamics care about that? Or more in general, are these pathologies enough to give up classical determinism? So, what do I mean with classical determinism? Well, simply the fact that you can predict the future if you know the past. For a discrete dynamical system with discrete time and states, you build determinism into the law. Otherwise, it could be, for example, a Markov chain won't be deterministic because it's a stochastic law. But if the law is deterministic, so is the system. For systems with continuous variables, in particular independent variables like differential equations, determinism is embodied by whether the conditions for existence and uniqueness theorems for solutions are satisfied. In the case of partial differential equations, in particular when they are hyperbolic, this is a very tricky issue. It's not obvious whether such theorems can be proved. When we have finitely many continuous variables, like in classical mechanics of point particles, for example, we have ODEs that control the evolution, and we know what conditions must be satisfied in order to satisfy an existence and uniqueness theorem, which in this case was formulated by Picard and Lindelof long ago. So general relativity not only is a theory with hyperbolic PDEs, is a field theory, but it's also a gauge Hamiltonian system, or that is a constrained system, meaning that not all degrees of freedom that one starts with the description of the system are physical. And determinism really will fail only if we have no way to evolve uniquely all the physical degrees of freedom. If something goes wrong with the gauge ones, that is not a problem that concerns physics. But what are the physical degrees of freedom on GR? Well, that's exactly what shape dynamics is all about. A mini history of shape dynamics as applied to general relativity. These wonderful people here worked on proving that the initial value problem of general relativity can be solved, because they found a way to recast it as a set of elliptic as opposed to hyperbolic partial differential equations. That's the type of equations for which existence and uniqueness theorems exist. And this can be done thanks to the York method, it's commonly called, but it's due to a long string of works by Andrei Liknarovich, Ivan Choquet-Brouat, so Nielo Murko participated in this story. So this can be done only if space-time can be foliated with a constant extrinsic trace of the extrinsic curvature, commonly called CMC foliation. In such a foliation, one observes that the reduced phase space, the physical degrees of freedom of the theory, are conformal 3 geometries, and of course their conjugate momenta, which are transverse traceless tensors. This is a strong indication that there is something special about conformal 3 geometries. Julian and collaborators in early 2000s were the first to really take this input seriously and proposed that we found a theory of gravity on conformal degrees of freedom, spatially conformal degrees of freedom. What we now work with and call shape dynamics was in its modern incarnation was formulated by Yiki, Sean, and Tim in 2010 in their paper about symmetry trading and general relativity. So shape dynamics was also very much inspired and based on relational ideas. Here I want to mention that too. There is this other string of authors, influential authors, that shaped, pardon my pun, our current view on relationalism. Ernst Mach, Poincaré, and most of all right now Julian Barber, and I wanted to place here also the late Bruno Bertotti, who was a wonderful person which we were missing very much. So temporal relationalism has been said in this workshop. We want to abstract time from change, and therefore only the relative change between physical degrees of freedom is what we perceive as time, and is what is measurable. Spatial relationalism, in the context of shape dynamics, implies that the physical degrees of freedom that I refer to here are shapes, which means they are independent of coordinate systems. That is, we have a spatial diffeomorphism invariance gauge symmetry of the theory, and they're independent of local scale, which means they have a local three-dimensional Weil invariance. So that's why we talk about three-dimensional conformal geometries as the basic objects of shape dynamics. So the physical content of shape dynamics, taking into account these two principles, is that the evolution of the shape degrees of freedom with respect to each other is all there is to physics. Okay. So now the question arises, this shape dynamical description of gravity, is it singular or not? Well, once we express physics in terms of the rate of change of one shape degree of freedom with respect to the other, the York method mentioned above gives us a procedure to map such solutions of shape dynamics into a space-time with this volume, which is not a shape degree of freedom, and fourth-dimensional structures and curvature invariance and momentum tensor and so on. So, is it the shape evolution that is singular in singular solutions, or is the singularity all in the map between shape solutions and space-times? In this latter case, determinism might be saved, because if the shape description is regular and can be continued uniquely through a singularity, we don't have a problem with determinism. We have a problem with the space-time description of physics, but not with the basic dynamical law. How to test this? The first interesting piece of evidence regarding what is the right way to try and check determinism in shape dynamics comes from the so-called BKL conjecture, Belinsky, Kalatnikov, Lifshitz. These people in 1971 conjectured that since the Einstein equations, in a loose sense here, you shouldn't take this equation I wrote literally. To be more precise, I refer you to this wonderful paper by David and Abai, and Anderson. So the spatial derivatives that appear in the equations, in some sense, near singularity, are suppressed with respect to the rest of the terms. So these people conjecture that the dynamics governed by partial differential equations tend to a dynamics in which no spatial derivatives are present, only time derivatives. And therefore, what people call velocity-dominated equations. And so we have essentially one independent system of ordinary differential equations per space point. And the problem is whether it can be proved rigorously that every solution of GR will tend to a solution of this ODE system. Here we're stepping a little bit out of the normal framework of the theory of partial differential equations. In what sense a partial differential equation can tend to an ODE? It's hard to say. There's a lot of numerical evidence in favor of the validity of this conjecture. And in the case of analytic solutions of GR, in presence of a stiff matter source, I will come back to this because it's an important part of my argument as well. For every solution of the velocity-dominated equation, there exists a solution of the full field equations, an analytic one though, that converges to the velocity-dominated solutions. This was proved by Anderson and Randall in 2001, and I think it's as close as we got to an actual proof of the conjecture, although not complete. So what is this? What do these ODE that the system tends to look like? Well, you can imagine that it's easy to imagine that they are just the equations of motion for the global modes, for the homogeneous modes of the gravitational field, because the homogeneous modes don't care about spatial derivatives. So if the topology of our spatial hypersurface is that of a three-sphere, a homogeneous ansatz gives us what is commonly known as Bianchi type 9 universes. And here I won't describe what the spacetime looks like. I will just focus on the dynamical variables. There's only three variables. One is the Sloan shape, because it's the three volume of our three-sphere. And I indicate it in blue as T. And the red variables would be the shape degrees of freedom. There are two anisotropy parameters known as Wisner variables, which determine the shape of our three geometry. And when there's zero, we have a not only homogeneous but also isotropic metric on the three-sphere, introducing their conjugate momenta to x, y, and v. The conjugate momentum to v is called York time, tau. We can write the only surviving constraint of the constraint system of the theory. It is the homogeneous mode of the Hamiltonian constraint. And it looks like this. It has a quadratic kinetic term. Forget that there is a dependence on the volume in this scale term, but this can be reabsorbed with a simple transformation if we really want the Hamiltonian in the form of that of a point particle. Essentially, we have a kinetic term plus a potential term. The potential term is composed of is homogeneous in the volume, and it depends like the volume to the 4/3. And the rest of it I call shape potential, because it's it depends only on the anisotropy parameters, and it has this form. So the dynamics of this is that of a point particle subject to this potential. And we can even see it as a two-dimensional point particle on the plane xy, and treat tau and v as separate dynamical variables. It will be useful to treat it like that, because then v acts like a coupling constant for the potential, which is time dependent. So I mentioned that shape dynamics is relational. Since this is a conference on shape dynamics, I want to show explicitly how in the simple symmetry reduced system one can see the relationalism of the theory. So x and y are shape degrees of freedom. They are ratios between lengths, and so they can be considered relational. What is a leftover of non-relationalism is the volume, the free volume. It's not a scale invariant. But the theory has two Lagrangian shape degrees of freedom and one Lagrangian non-shape degree of freedom. But it also has one first-class constraint, the Hamiltonian constraint, which is a consequence of reparametrization invariance. This means that the physical degrees of freedom are one less. Therefore, I can entirely describe the system in terms of relational degrees of freedom. This is the point. One convoluted way to do it, Dave will show a much more elegant and simple one, is to, in the spirit of symmetry trading, what we call symmetry trading in shape dynamics, we can trade the refoliation invariance of the theory for full conformal invariance. Where tau is monotonic, and in the Bianchi IX system it's always monotonic, we can use it as an independent variable. Tau is a sort of dilatational momentum of the theory. Then there is an Hamiltonian that generates tau evolution. It's just a solution of the Hamiltonian constraint with respect to the volume, which is canonically conjugate to tau. And since it's a third order polynomial, the solution, there is only one positive solution, and it looks like this, rather cumbersome. And it depends on px, py, tau, v, and x and y, of course. However, formally speaking, we can work with that. And so we have a tau-dependent Hamiltonian, a non-autonomous, that gives rise to a non-autonomous system of equations. I can, but the volume has completely been expelled from the description. We don't need it at all anymore. To remove tau2, there is a non-canonical transformation I can make, in which I multiply essentially the shape momenta by the York time, together with the reparametrization to the logarithm of York time, that entirely removes tau from the right-hand side of the equations of motion, giving rise to a set of autonomous equations, which, however, the price to pay is that the appearance of a dissipative term, something that is proportional to the momentum that is evolving. And this is a non-symplectic, non-canonical term. The equations are not properly Hamiltonian. They are Hamiltonian plus a term. This can be recasted in the form of a metric, so-called metriplectic formalism, which on top of the symplectic form, we also have a metric. And it's interesting because it gives rise to a notion of entropy that is enters as a further canonical variable. But anyways, it's interesting, but all of this has been superseded by David's recent formulation in terms of contact geometry and the variational principle of Burgos. So I just recommend that you stay connected for David's talk. The point is that I can show you this way that if I'm only interested in the change of one shape variable with respect to the other, for example, how much x changed when I change infinitesimally y, I get a set of differential equations that do not depend on either tau or v. So this is a truly relational description now of the system, without any reference to volume or York time, non-shape degrees of freedom. Okay, this is very formal, and it's not even that useful in order to prove things, because the other descriptions we have at disposal are often the non-relational description might be better in certain situations for calculations. So let me show you how the dynamics of the Bianchi IX system look like. This is the potential, the shape potential. And I wrote it in terms of this function. As you can see, it's the sum of 6 terms, which are all exponentials in x and y. If we plot it, it has this symmetry, this threefold symmetry. It looks like a Mercedes star, someone likes to call it like that. And if I give you a 3D plot of the potential, you can see how the potential walls are extremely steep because it's exponential. So it looks like more of a wall than a potential, than a smooth potential. The solutions, therefore, when a potential is very steep, you either have much more kinetic energy than potential energy, or whenever they start looking at each other, kinetic and potential energy, you have a bounce, a very sharp change in trajectory. The metaphor I like to use is that of a particle in the xy plane with a potential wall that is shaped like a triangle, and it is receding in time. Why is it receding in time? Because there is this coupling with the volume, and the volume is going to 0 as I evolve towards the singularity. And so I evolve like I interpose straight uniform motion, what is known as Kasner epochs, with sharp transitions, sharp changes in trajectory called tau transitions. They're almost elastic bounces. They would be elastic if the volume was conserved, but it isn't. Since the coupling is receding, is decreasing as I evolve towards the singularity, my particle will keep exploring larger and larger regions of shape space. We'll go further and further from the origin. I use this parameter time t, that is just an independent parameter that appears in the equations of motion. When it goes to infinity, I'm reaching the singularity, okay? As I go to infinity, the particle explores increasingly larger regions, and therefore at the singularity, I essentially start exploring the border of shape space, which is composed of degenerate shapes that are effectively bidimensional or one-dimensional. Julian calls them cigars or pancakes. I don't know where he got it from, but you get the idea. Something in which one direction is completely squished, or two directions are completely squished with respect to the other. Interestingly, since they are effectively 2D or 1D, they cannot support a non-zero volume. Therefore, the singularity is a locus in shape space. There is a place in shape space where I can only be singular because I cannot have a non-zero volume. However, one problem is that the bounces never end, because it's true that these potential worlds are receding, are flying away, but they never recede fast enough so that the particle won't catch up with them. Therefore, if the Big Bang is reached at T equals infinity, there will be an infinite amount of bounces in a finite proper time, because you can easily prove that from any finite time to the singularity, although there is an infinite parameter time, the elapsed proper time is finite. So this starts something like a physical singularity, no? I can focus on some shape variables. For example, write x and y in polar coordinates and focus on the angle. That tells me the direction towards which I fly when I'm reaching the boundary of shape space. Well, this variable oscillates infinitely fast in a finite amount of proper time near the Big Bang. This is what mathematicians call an essential singularity, because it's similar to what you get if you try to do the limit for x that goes to 0 of the sine of 1 of x. The prototypical essential singularity oscillates so fast that you can't really preserve any data, for example, about the derivatives of any order of the function. Interestingly, the same happens in the analog of the Big Bang in a Newtonian n-body problem. This is called a total collision, in which all the particles hit each other at the same time. And with Paula, we wrote a paper on this and found that that particular type of singularity is again an essential singularity. And this is like the second most popular example of essential singularity, when you take the limit of the exponential of 1 over x. So all the information about all derivatives is washed out. So it seems like there is something to the dynamics of gravity that wants to kill information, the differential information you can get from your physical degrees of freedom. So in this paper about continuation through the Big Bang with Tim and David, we argued that the fact that the singularities at the finite proper time should not be taken too seriously. And actually, since we want to understand time as change, not as something external to the system, well, we could argue that there is an infinite amount of change between any finite time and the singularity, because there is an infinite amount of shapes that the system goes through. Moreover, proper time, which we said takes a finite value of the singularity, cannot have its usual physical meaning near the singularity. Because normally you have a smooth space-time, and a physical clock has to be an extended object, maybe very small, but it has to have some extension in order to have structure. And usually you approximate the reading of the clock with the proper time along a certain time-like world line, like the central mass of the clock. And they two match. The problem is that near a singularity, the forces, the tidal forces of the gravitational field are so strong that any extended object will be tear apart, will be broken down to its pieces and carried around the whole manifold. So we cannot really say that the reading of the clock keep matching with the proper time. There actually doesn't make much sense to talk about the reading on the clock anymore. And if all we're interested in is time has changed, well, there is an infinite amount of that going on. So, okay, we argued that yes, there is an essential singularity, but one should, in some sense, understand it as happening in an infinite past. However, there is a whole class of solutions, of physical situations in which this essential singularity is not present. Those are called quiescent solutions. And this is what we discussed in the paper I mentioned, the PLB paper. Adding a homogeneous scalar field, it's a simple addition to the Hamiltonian with its little potential here. If the potential doesn't grow too fast, which means that as phi goes to infinity, it grows slower than an exponential of the field. we can prove that after a finite number of bounces, the bounces will stop and the solution will settle on a particular Kasner straight line type solution. So something like this. You have a whole bunch of chaos and bounces, and then after a last bounce, the system settles on a straight line solution forever until it reaches the boundary of shape space. This makes the singularity regularizable. I must mention the addition of this scalar field is a type of source that is called stiff, in the sense that it has an equation of state, a particular equation of state, and it is the kind of solutions that Anderson and Randall proved the BKL conjecture to be valid for. Okay, so how do I regularize the singularity? Well, first I have to extend my shape configuration space, because the metric variables famously are blind to the orientation of my manifold. It's the frame field variables that know about the orientation, and this is quadratic in the frame fields. The determinant of the frame field is, if you want, a shape degree of freedom that hasn't been considered so far. What we did is to represent the two orientations and their shapes into two planes, two Misner planes of variables x and y, and we glue them together into a single shaped configuration space by using what we call what is known as mnemonic projection, which means that each point in each plane is mapped through this map, this projection, into one hemisphere of the sphere. Therefore, at the equator of this two sphere, I will have the degenerate shapes. Here I will have the positive orientation shapes, and here I will have the negative orientation shapes. So this is what the shape potential looks like when I project it on the sphere. And I can cover the whole sphere, or a region of the sphere that covers the equator with a coordinate patch. For example, spherical coordinates on the sphere. So at the equator, I have these degenerate shapes, which are effectively 1 or 2 dimensional. And I shouldn't really think of these degenerate shapes as singularities of my shape variables, because imagine that I'm considering a 3-body system, 3-point particles, and I'm using the area of the triangle represented by the 3-body as one of my dynamical variables, and then some angles or not. When the particles become collinear, the area is 0. Why? Because a segment cannot support any area, any non-zero area. And the system evolves through this collinear configuration very smoothly. The area goes to 0 and bounces back, but in a particular way that does not violate determinism. And this is the same that we think is happening here. The system will go through a 0 volume configuration that is effectively 2 or 1 dimensional, and goes through smoothly in the sense of the shape degrees of freedom with the opposite orientation. The same happens in the 3-body system. The orientation of the new triangle after the collinear configuration is changed. So this is what a Kasner solution looks like. It's a straight line on the Misner plane, and it maps onto half a great circle on the shape sphere. It is quite natural to imagine that we can continue this great circle uniquely into another great circle on the other side. And that's what happens. And it projects onto another straight line Kasner solution, which, as you can see, is not exactly the same solution. It's on the other side of the potential. So Kasner solutions can be continued uniquely, but the dynamics is richer than just the Kasner equations of motion. Well, what happens is that for quiescent solutions, we have a complicated Bianchi IX dynamics, which at the end settles onto, this is the yellow curve, it settles onto one great circle, one Kasner solution, and it approximates it better and better. And then it crosses the equator and goes on the other side and develops into another Bianchi IX dynamics. This is proved by the equations of motion, because they satisfy the conditions of the Picard-Lindelof theorem, so the uniqueness, existence of uniqueness of solutions around in a neighborhood of the equator. If we want to be more daring, we can even argue, following this paper with Julian and Tim, that if generic initial conditions are chosen at the singularity, then the system away from it will develop a thermodynamic arrow time, actually a thermodynamic arrow time, that will point opposite ways. So the picture that I get is that of two expanding universe with opposite orientation coming out of a single common Big Bang, which is on the path of both. Okay. So the result is, as I said, requires stiff matter, which the simplest example of stiff matter is a scalar field. And of the standard model and standard cosmological model fields, only a scalar fits the bill. The others will not give you quiescence. Interestingly, slow roll inflationary potentials certainly do satisfy the condition for quiescence because their potential goes to a constant at infinity. Even more intriguingly, I considered in a paper the Starbinski potential, which is consequence of assuming an effective action for gravity that includes the first lowest order quantum corrections to general relativity in the sense of an R² term in the action. This was done by Starbinski in 1979. And the potential, this can be recasted as a system which is a scalar field minimally coupled to Einstein gravity. And the potential of this field has the same form that goes to a constant as phi goes to infinity. Moreover, this particular model sits right in the middle of current observational constraints from the early universe, so that is exciting. Let me rephrase what I'm trying to say here, that our best understanding of how semi-classical gravity works at the during inflation and before is a model that exhibits quiescence towards a Big Bang. So that's pretty exciting to me in terms of continuation, my continuation results. So I just wanted to mention it. Okay, I talked about Big Bang singularities, but we know at least another type of singularity in general relativity, actually much more. The next obvious one to consider is the singularity at the center of black holes. With Dave, we recently put out a paper in which we consider a model of the interior of a Schwarzschild black hole, known as the Kantowski Sachs model, in which I model my space-like hypersurfaces as a homogeneous cosmology with the topology of a two-sphere times their real line. We have only one shape degree of freedom called W in this case, and the Hamiltonian constraint looks like pretty much like the Bianchi IX one, except that I have one instead of two shape degrees of freedom. So W is this shape variable that measures how big is the two-sphere compared to a segment of the R part of the geometry. The solutions all look like this in the VW plane, and like a point particle that bounces off a potential, an exponential potential. And in one direction, I go towards the singularity, in the other, I go towards the horizon because I can only describe the interior of Schwarzschild. Each of them, as a space-time, is completely isometric to a Schwarzschild interior. It just changes the type of coordinates that I'm putting on this space-time. So the Hamiltonian constraint is pretty much like Bianchi IX, except it's one-dimensional. So, for example, if we stick on a symmetry direction of the shape potential, I can symmetry reduce the problem. For example, I can put x and px to 0, and I get an Hamiltonian that is pretty much like that. And there is no chaotic behavior because there is not enough dimensionality of the system. So no need for quiescence. Essentially, if I do the mnemonic projection here, I get a circle. And if I express my evolution as one shape degree of freedom evolving with respect to the other, I only have one shape degree of freedom. All I can do on a circle is walk. Of course, I will walk through the equator. So the solution, technically, the proof is rather trivial. The tentative picture we drew in the paper is this, that of The gray area is the part of Schwarzschild covered by the Kantowski Sachs model. This is the singularity. I continue it into a region with an opposite orientation, which is the interior of essentially a white hole geometry that shares the singularity with my black hole geometry. Now, since the result is too trivial, well, we thought that what we're really interested in is checking whether all of the physical degrees of freedom of the system will continue deterministically through the singularity. So we need to at least add one shape degree of freedom, otherwise, and the obvious choice is a homogeneous scalar field. In a Kantowski geometry, a homogeneous field means that it's spherically symmetric. And so again, I add my scalar field, and I double, therefore, my shape, the dimensions of my shape space. And again, I put this two-dimensional shape space on two planes for the two orientations, and I can perform again my mnemonic projection and write the equations of motion on this sphere. And well, it turns out they satisfy the Picard-Lindelof theorem. Therefore, I can continue through Schwarzschild singularity and carry all the information about the state of the scalar field too. This is a page with a future outlook for black holes, but I don't want to dwell on it. I'll put it here so that it's recorded and people can read it. Maybe we can discuss it in the discussion, because otherwise I wouldn't have time to mention gauge fields, which is the latest project in our quest to save determinism. It's with my student, PhD student Martin Adamo, and my master student Vishal Jha. We added to the Bianchi IX model gauge fields, like electromagnetic fields, that satisfy, again, the homogeneous ansatz. These are constant vector fields on the three sphere. At the beginning, I thought this couldn't be done because ignorantly, I was assuming that, as mathematicians say, one cannot comb an orange. As in, there are topological restrictions to global, smooth, non-zero vector fields on a sphere, as is illustrated by this picture. As you see, oranges are obviously uncombable. The fact is that I was ignorant because these results only regard even dimensional spheres, so a two-sphere like this one. In truth, odd dimensional spheres admit continuous non-zero vector fields. And for example, the three spheres, which is what we're interested in Bianchi IX, do admit these fields. And if you assume that this field be homogeneous, so translational invariant, they will admit three linearly independent degrees of freedom for the vector field. So three shaped degrees of freedom. Another worry you might have is, why are there three? I thought, you thought that the electromagnetic field had two polarizations, not three. Well, locally that's true because there is the Gauss constraint that kills one degree of freedom. But the homogeneous mode of the Maxwell field satisfies the Gauss constraint automatically because it's homogeneous. Therefore, global topological degrees of freedom of the Maxwell field on the three sphere, they are three. So it happens. So we end up with a theory with three geometric degrees of freedom, the two Misner variables that are shaped and one volume, plus three gauge field degrees of freedom, which are all shapes. The Hamiltonian constraint now takes the form of the usual Bianchi IX Hamiltonian constraint plus two terms. One that is looks like the usual Maxwell Hamiltonian. It's just multiplied by a diagonal but non-identity matrix, depending on the shape degrees of freedom, and it's all multiplied by the 2/3 power of the volume, which suppresses it near the singularity. The other term is again multiplied by a diagonal matrix, and it involves these cross products of the electric and electric field and then electromagnetic potential. And this matrix depends on the shape variables, but is not suppressed by any power of the volume. So at the singularity, this could be still influencing the geometry. However, one can prove that Sij near the singularity as p goes to 0 And in particular, as x and y go to infinity, Sij goes to 0. So for example, I can write it in polar coordinates on shape space. And when rho goes to infinity, so where I reach the boundary of this plane, this goes to 0 except for 6 particular directions, which are the symmetry directions of the potential, the shape potential. And so essentially it goes to 0 almost everywhere. These need to be treated separately. So almost everywhere, almost every solution will see the gauge field decouple from the equations of motion of the geometric degrees of freedom. So what happens is that the geometric degrees of freedom, x, y, and the volume, will appear asymptotically, will appear on the right-hand side of the equations of motion for the gauge field, but not the other way around. The gauge field will not influence the geometry. This is a phenomenon that Wheeler, who was the master of aphorisms, described as the fact that near a singularity matter doesn't matter, at least for standard model matter. So matter fields are along for the ride. The geometry tells them how to evolve, but doesn't accept feedback from them if you want, okay? So all of this is enough to prove that the continuation result has to extend to electromagnetic fields too. All right, I'm basically out of time, so let me conclude with an outlook. We are collecting evidence that the singularities of the Big Bang or Schwarzschild spacetimes are not the end of classical determinism, but rather they seem to represent an interface with a universe or a pocket of the universe with an opposite orientation. In the case of the Big Bang, we can argue, if we like, that the other universe might have a flipped arrow time. In that case, we would restore a sort of PT symmetry, and if, sorry, of a CT symmetry. If we add the electromagnetic field, we can extend it probably to P2, and that would be interesting for cosmology, I guess. In Schwarzschild, I don't think that we can argue that we have a flipping of the arrow time, because we can only set generic initial conditions once. If we do it at the singularity of the Big Bang, we can't do it again when a localized region like a Schwarzschild black hole goes through a singularity. So the result is established for quiescent homogeneous cosmologies with any number of homogeneous scalar and gauge fields, and for Schwarzschild interiors with spherically symmetric scalar fields. With the BKL conjecture, we can argue that the results should extend to arbitrary inhomogeneities. Also because this Anderson-Randall paper works precisely for quiescent models. A different issue is whether one can devise a computationally efficient algorithm in order to connect initial data on one universe and the one on the opposite orientation one. We would like to have a general theorem in the spirit of Penrose, Hawking, singularity theorems, but of course we don't have that yet, and I don't know how far we are from formulating one. I leave you with this slide and with a list of references for further reading if you're interested in, and thank you. This would be all.
Yeah, thank you for the great talk. That was really fascinating.
How do I stop sharing?
I can stop for you.
Okay, thank you.
Okay, great. So that was really fascinating, also very dense. I would have a couple of questions, but let's take questions from the audience first, if there are any. Okay, until people can, collect their thoughts, let me just very quickly ask, when you talked about the conjectures that you have, again, the Janus point pictures, a picture with two opposite arrows of time, what quantity plays the role of complexity there?
So there is a conjecture, I would say, probably due to Julian or Tim or linear combinations thereof, that it might be the Yamabi constant.
Sorry, the what constant?
The Yamabi constant. So that is an object that is of interest in conformal geometry, and so it measures essentially how far the conformal geometry is from that of a three-sphere. This object in homogeneous cosmologies can be shown to coincide with the shape potential, that U of xy that I wrote. And in effect, when what the geometry does, what the shape do is that the closer you get to the singularity, the larger regions of shape space you explore, and eventually you go infinitely far from the origin, which is a spherical three-sphere geometry, and therefore this Yamabi constant will diverge there. So, and it actually does behave, does grow monotonically away from, so as you approach, when you reach quiescence, essentially. When you're quiescent, the thing is evolving linearly and it grows. But anyways, also statistically, you explore larger and larger regions of that potential. So yeah, that seems to be in line with Julian's strong intuition that we have complex. If that is what you would call complexity, it looks like it is evolving more or less. It's growing on average, and in certain situations it's even monotonic. Yeah. Julian wants to intervene on this, but
yeah, I just want, well, first of all, I would say Tim made that remark immediately. I mean, I put to Tim back, I think it was in about 2000, yeah, it was 2012. I mentioned the idea of the complexity defining a direction of time, and Tim immediately said, well, there's an analog of that. I think actually technically what you mean is the Yamabi constant rather than, I mean, it's a
the same variant.
Wait a minute, which one is the constant? Is the one
constant that is not constant.
Yes. Anyway, the main thing is just like the complexity is a function on shape space, and the Yamabi thing is as well. And what I think is, if the idea is really going to have traction, I think we want to say that there is something analogous when you take into account all forms of potential energy. So there is Martin Lesud, who is now with Yao in Harvard, pointed out to me, discovered a paper which extends the Yamabi idea to include a scalar field under certain circumstances. And I've conjectured for a long time that this should be something which I call Yamabi plus matter, which would be all the known potential energies in physics made scale invariant. If that were the case, then I think this would be very, very interesting. And if that increased monotonically from the Big Bang all the way, I think that would really strengthen the picture.
As a further remark, if I may, pay particular attention to Dave's talk, because one thing that, or don't, he doesn't want to. One thing that might be relevant here is the interesting connection between the friction that these systems show and the fact that you explore larger or smaller regions of your potential energy. No? If you lose energy or gain energy through friction, you're exploring larger regions of your potential. And if this potential has something to do with complexity, you see, you have a sort of statistical argument towards the increase in or decrease in complexity. So yeah, maybe we can rekindle this discussion after his talk.
Yeah, thank you. I think I'm going to stay for David's talk. Let's go to Oliver Pooley's question.
Thank you. So can you say a little bit more about how seriously we should take the different orientations as genuinely distinct configurations? So do you think of them as defined relationally with respect to each other? So if you've got a continuation through the singularity, you can sort of try and have a relational understanding of the difference, because as you'll know, going back to Kant's criticism of Leibniz, distinct orientations you would think are relationally intrinsically the same, but
yeah, well,
it sounds like you're not treating them like that.
No, and to be honest, I didn't invest a huge amount of thought in that, because I just thought, look, we have Madame Moore's experiment, and parity is not a property of nature. We can distinguish right-handed particles from left-handed particles with an experiment. So I was assuming simply that if you had the whole standard model in your description, the parity breaking term would allow you to differentiate between the two orientations, right? So maybe I was being simple-minded, but I think that should pretty much settle it. I don't know. I've seen a lot of raising hands, so maybe people have different ideas on this, but go ahead.
So Tim's hand is definitely raised, I see.
Yes. Well, let me answer that. I mean, I think Oliver is completely right that orientation by itself, if it's the only orientation, you cannot relationally observe it. What you need is, so when we say we can distinguish left-handed from right-handed particles, we do that on the basis that we have electrons here and that we have a particular sense of orientation here, and that's our reference system. So what you can objectively say is you can compare two orientations. So now, Flavio, this is why I'm interested in seeing when the paper comes out about the global gauge degrees of freedom, because there you can really compare orientation of the frame field with respect to the orientation in which the vector field is expressed, and see whether that relation flips or doesn't flip. So that was, and actually this was a comment based on the previous question that I had, and the question that I actually had is related to that, which is, do you have any idea, or you and Dave have any idea how to extend any more global degrees of freedom in Kantowski-Sachs?
Well, except from the obvious, making the gauge field non-abelian, and well, fermions, for example, could be an interesting thing to look into. There should be a global, a homogeneous fermion in the sense of the translational invariance of Kantowski-Sachs. That's one. And then of course further, well, then there is no inhomogeneous degrees of freedom, but you mentioned homogeneous. I think that's really gauge fields, abelian or not, and fermions. That's the next step for me. Now, if Dave wants to complement this answer, go ahead.
Yeah, I mean, what you've said is completely correct, Flavio. I'm completely on board with that. I think you're entirely right. I have one minor comment, which is that for the love of God, for the health of your graduate students, do Bianchi 1 before you do Bianchi 9. It's so much easier, please. You know, I mean, even do FLRW, right? It's really so much simpler. And when you introduce these magnetic fields, you've got enough degrees of freedom, as I did with scalar fields, to have shapes that continue past the singularity. So I think that in and of itself would be interesting and would probably be enough to answer Oliver's question about orientation flips without having to go through the, you know, I mean, if you remember when we did this, sorry, this historical for everyone who looked at it, like it's Bianchi 9 is hard. The reason Flavio's presented Bianchi 9 here is that it's the hardest one to do. The results we've got apply to all Bianchi models, and the BKL conjecture just says you end up with one of them, with Bianchi 9 or 8 being the most generic. But if you can prove the continuation in 9 looks a lot like the continuation in 1. So if you can do the continuation in 1 first, it will be enough to answer in principle the question about orientation flips.
This is a very good comment. Thank you, Dave. Unfortunately, now my PhD students will have heard that, so I can't force them to do the hard thing anymore, but whatever. But yes, this is something I didn't have time to mention, but of course I'm interested in Bianchi IX also because the BKA conjecture says that I get an infinite amount of Bianchi IX, one per point. But Bianchi IX tends to one particular Bianchi I universe. And that is a computationally very efficient way of doing things. And therefore, it's likely to be our favorite description of the ultra early universe, right? And it's the natural place to work with. Bianchi I is non-curved, it's flat. The connection is trivial. It's immensely more easy. So yes, that's a natural framework to do.
Homogeneous vector fields in 3 space are easy to understand.
Are constant. Yes, they're literally constant. Yes, so very good point.
Yes, thanks. I'm also glad to know that if I want to understand this better, I can start with a simpler model.